Maybe start. So you will need this account for which you need these files. So once you have it, so till then, so what you can do is maybe ask the section.
Sim, sim. Duas fazemos o nós podemos só. Então. Mas agora, eu acho que ele está a pensar que eu quero fazer a eliminação do código de demonstrações, não é o conceito de demonstração direta. Desculpa, porque ele vem cá, não é? Portanto. Pois não. Vem cá no julho. Posso ir?
Sim, 14 de fevereiro. I don't understand because
Mas hoje, empresta-me um livro do revista 2. Sim, sim.
Não, é provavelmente não.
Assim, quando você a fazer um seminário, eu à vontade. As partes do que a gente já sabe.
So have you ever studied term rewriting systems?
A little bit. Of course, at the beginning of my case, the last time I experienced.
Okay. So about this simplification orders, techniques for termination. You study those stuff?
It was a little bit of the basic ones, Grover basis for simplifying.
Okay, Grover.
Yes, I have.
So you should use this.
There's this book, term rewriting and all that, by a guy. One of the authors is also the author of Isabel, which is this proof assistant. Also, so there's this computer language standard ML. I think there's a guy like Lawrence Paulson or something who wrote like a book about it, and he's also one of the authors of this Isabel. But I've never studied stuff. So.
The one for me is.
But,
I can
say your friend or find your seeing the scene.
no, like I
Which
can
one were you going to be?
yeah, when I will be the one that for maybe that if the contract start maybe I will be like I will do some them in and I think that it's carried out by that.
So I wanted to make a small introduction actually. Why I'm particularly excited for this talk, because Francesca is here. Have you met?
no.
So she started her PhD just a couple of weeks ago.
With you?
With me, and she will need you to do a very gentle introduction to what you are doing, right?
Yeah.
Because I don't know if you ever had first order logic.
Yeah.
You had. Well, that will help.
Okay.
So
This is going to be absolutely very easy, I assure you.
So what Lewis is going to prove is he's going to prove something like there's a particular function which has super constant growth, and he will tell us what the function is, right? The function has a very simple combinatorial definition, right, which he will present to us.
Yeah.
And the remarkable thing is that in order to prove that this function has super constant growth, the only known proof uses these very strong axioms. So these are axioms in set theory saying that a certain large cardinal number exists. I'm assuming that you don't even know what a cardinal number is, so you should.
Yeah. Yeah.
I thought so, yes.
Yeah. Yeah. I'll review all of that.
So although this function has very simple combinatorial definition, the proof that it grows arbitrarily uses these very strong axioms that are independent of the usual axioms. Well, actually, they're not known to be independent.
There are new developments, and yeah, they are not. They are independent of piano arithmetic.
Okay.
Even by one comprehension.
Okay. So they should be independent of this set of axioms that we use. Certainly, they're independent of the kind of axioms that you will find in when you study complexity. Okay. So this raises upsetting, perturbing, very sad if true possibility, which is that there is this other function which we are very interested in. So suppose that Fn, instead of being the function that Luis is going to talk about, let me write it. Fn is the minimum C such that the set problem for instances of size n can be solved by circuits of size n to the c. So that it's not, it's some other effect.
Cannot. You want to prove that cannot.
Right. The definition is correct. The definition is correct. No, this is correct.
The minimum C might be.
Right. So, right, so this question is equivalent to proving that this F is super constant. So the problem we care the most in our area is a question of this form. We have some function which has a simple combinatorial definition, right? And we would like to prove that it grows super constantly. Now suppose that tragically, the function has this problem where it's actually independent. I mean, we cannot prove that it grows super constant without taking some big axiom from set theory, or maybe not even. Maybe it's independent even of this axiom, we don't know. Here's the point, that intuitively, if something has a simple combinatorial definition, this shouldn't happen, right? Because it's just combinatorics, right? You some very trivial, right? A plus B equals C, 1 plus 2 equals 3. So this should not happen. But Luis is going to give us an example of a situation where it does happen. Okay, and that's why I'm very interested, why I think you now and the audience maybe is also very interested. And so we're going to do that. And he's just going to take his time. Thank you for doing this.
Oh, thank you for coming. Yeah. So I think I look at this more your F as the search for a counterexample. So your input would be in your case a C, and then you're asking for the minimum counterexample. So this is why I was thinking. So define G of C as the minimum n inside MC.
Yeah.
So it's the same thing.
That's f of n plus 1, okay?
Yeah, I guess, yes, I suppose so. I don't know.
Or right, good.
But the way I would approach it would be like this, the search for a counterexample.
It's the minimum n such that. Oh, I see. Oh, no, I'm wrong.
Would be,
I see. Minimum n such that. Oh,
it's the same thing. So you also want g of n or g of c to grow to infinity. So, well, so let's.
no, wait. So there's a problem here. Are you? I think that it's an omega 1 if we have f is.
Yeah.
So if set is in K. I see. So this will happen for all large n. So this will be fine. I see. Okay.
I just mentioned this because it's the way I think. I would approach the, but also one should say that P might be very different from Impal. Well, we know it's different, but because this has uncountably many things, but these two things may be very different animals. So here we're inviting combinatorics, and here we're more on a more controlled setting.
So can we write? Can we write? So there's these two statements: f of n is omega 1.
Yeah.
And g of n is omega 1.
Same, yeah.
And are they the same arithmetic type statement?
Yes. I02.
They both so looking out why is that for every number I.
So for every program and for every polynomial, there is a counterexample. So yeah, so for every there is a for every candidate, there's a counterexample.
Candidate one.
So for a program and a polynomial, there is a C, well an S, since it's a string, and S is S, and the program is wrong about S.
No, that's not what you can. No, but the statement, like, if you just write down, I know that this is equivalent to f of n and g of n equal omega 1, but if you just write that statement naively, f of n is omega 1, and g of n is omega 1.
Yeah.
So what does that mean? For every natural number, there exists some c such that g is at least this.
Yeah, some string for which a circuit is wrong. So, hello, everybody. That's so I saw that Charles was there. Hi. So I'll start with saying what are Laver tables. So I gave a lecture last month where I talked about this thing. So so when I say last month, it refers to that, but I won't use anything of what I said. So the last self-distributive law, is this: A star B star C equals A star B star A star C. So obviously, if you think on multiplication and addition, then you would have multiplication and addition, obviously. So I'll just use LD as a left distributive. So first observation, this operation is not associative in general. So the A star A.
So if an operation is only acting if that is self-distributive.
Yeah, sorry. Yeah.
It's not nothing else.
Yeah. Is this well, in general, this happens. So it's not associative and it's not not commutative. So here we have an example of a left power, and here we have an example of a right power. Left in the sense that you start associating on the left, and right here is on the sense that you start associating on the right. So, and as a definition, in general, the left powers are defined by recursion. So they have this notation. So the first left power, just A, and then AN plus 1, AN star A. So if you have a string of A's, you start associating from the left. And the right powers are defined, they start the same, but then you associate on the right. Sorry, N plus 1 is A star A N. So as an observation, the left power over 2 is they're equal, and as you can see, this.
I'm thinking of something like
Sorry.
because you're thinking of A star B as something like A to the power B or something like this.
Yeah, well, in general, when you have a product, one talks about powers. If you're iterating the same, if you're in a group.
Yes, but it's just that I would have called left powers to the bottom one. Right?
Yeah, me too. Yeah, but this has become a standard. So we think so. Left, as in start associating on the left, like in lambda calculus. And right, if you start associating on the right. Now, an example where this appears naturally is if you have a group, you can define the following operation. Just conjugation. And this is left distributive. So there's absolutely no lack of left distributive outcomes.
So you're fixed enough before then when you're defining the star operator.
For any two, yeah. So you're thinking on the LF kind of, yeah. So, and it's easier to prove this left distributivity if you start from the right to the left, because then things cancel by themselves. If you go from the left to the right, you have to guess, while it's from the right to the left, it's mechanic. But there's a catch here, is that here in groups, this operation is just F star F will just be F, because the F will cancel, and so this is not the cases that we are going to look at. So as a convention, so in this talk, I will only talk about LD algebras with one generator, which means so the smallest subalgebra that contains a generator is the whole algebra. And since it only has one generator, so there only this trivial algebra it comes from a group. So the algebras that I'm going to talk about, they do not come from groups. Yeah.
When you say a generator, you mean there's some element A, and you're allowed to take A star A, and you can
do all these left, right, anything, and then it will generate the whole algebra. So how do we go about building this stuff? So consider an element which is going to be the generator, and then consider its left powers. And suppose this was a group, and you have a cyclic group, and you eventually go back to where you started. So you can think that this happens. And you go back at stage n+1. So what would it look like, something like this? It's better if I do not erase. Sorry? Yes, I'm looking at finite. I think I can erase this. So start by identifying GI with the numbers. With the numbers. So what we have is I star 1 is just I+1. And we look, and for example, suppose n is 4. So 1, 2, 3, 4. One, 2, 3, and 4. So I'm saying that the left powers, so I star 1 is 1. So here, I will just just generate the group, and then when we reach n, we get to 1. And
just because you reach 1 doesn't mean that there are no more elements in the.
I'm trying to. So we will see that there are no other.
The 1 is the generator.
Yes. So 1 is a generator.
So let's try and build a table where 1 is the generator and the thing has size 4.
Yeah.
So we know when we do 1 times 1 times 1 times 4 times, it's going to be 1 again. Right? So let's call the first thing that we get 2, the second thing 3, the fourth, the other thing 4.
Yeah.
Right? Now you're going to tell us that we can actually fill the rest of the table just from this.
Yeah.
Starting.
Yeah. So how do we do this? So consider a particular case of this rule, which is substitute C by 1, and then let's look for so we will be able to fill this by starting at the bottom and going from left to right. So, for example, we know what's 4 star 1. So now, for example, we want 4 star 2. What we do, well, 2 is 1 star 1. So we apply the rule, and then we get 4 star 1 star 4 star 1. But what's 4 star 1? 4 star 1 is 1. And what's 1 star 1? 1 star 1 is 2. So here, you put 2. And you can go with 4 star 3, and it's 3 is 2 star 1. Four star 2 is 2. 4 star 1 is 1. And 2 star 1 is 3. And then you can see that here you got a 4. And so 3 star 2, what do we do? So we're now filling in this other row. Well, we do the same thing. It's 1 star 1. This is 3 star 1 star 3 star 1. 3 star 1, we know it's 4. And 4 star 4, I told you it was also 4. And if you continue, you will see that this is it gives you 4. Now there is a more algorithmic way of looking at this instead of just expanding, which is the following. Look at it. So I want to fill in a row A. And I want to fill this by recursion from, so I know what A star B is, and I want to go to the next element. What do? I look at the A plus 1 column, and I look what's in this row.
First of all,
Yeah.
A1.
A plus 1 column. So for example, 3, what's the 4th column? 4th column is this one, right? And what was on the 4th column? Just this 4. So these 3 were not filled in.
Sorry, so you're doing A star, B star 1.
Yeah. So A row column.
Oh, so A star 1, you already know what it is, so you can look at that column.
Yeah. Well, it's not all filled, but it's filled where it needs to be. In this case, it only has this 4. And then what you do is you look at the element, and you look at the row at the intersection. Sorry.
When you say this one, so now you're doing A equals 2.
Okay, so I'll do, yeah, then I'll do, yes, because it's clear then. Okay, row 2, you go to column 3. Yeah, 4 and 3, right?
Yeah, so 2 times 1.
So
You're starting from the left, so 2 times
yeah.
2.
So I want to fill in the row 2. I look at column 3, and then I go by recursion. What's the first number that's on row 2? 3. This tells me that I'm going to this column, and I go to the row 3. What's in the row 3? Column 3, row 3, 4. And now I go to the same column, but now I go to the row that's represented by this number, which is the 4th, which is 3. And now I continue in this column, and but now I look at what's in the row 3, which is 4. And I do the same with 1. For 1, I look at column 2. Column 2, then I start row 2, which is this, so it's 4. Then I go to 4 tells me I should go to row 4, which is 2. And then 2 tells me that I should go to the second row here, which is 4. So this is a more systematic. So if you do this, it's going to end up being the same, but this is more systematic. So you use the information on columns to fill in rows. So it's a really you cannot get more basic than this, without being totally trivial. But
so you're saying I have some. I'm doing a new role. That's A. So now you're saying that I always split. So to put 4 different B's, right? So I always put the 1 out, so that tells me the column.
yeah.
Right? So now, when I do B equals 1, I have to find out. Oh, we already know A star B is 1, so I just look. I see. So that gives me the row. And now I know what A star B equals 2 is. That's what I was filling. So whatever I put there, that gives me the row, and I can just keep doing it. So what you're saying is that in the end, the column that I'm fixing is some kind of. It's not permutation maybe, actually, because there could be repetition.
Yeah, there will be lots of repetitions.
I see, but I get the numbers from the particular column, right? Namely, this row plus 1, or not plus 1, yeah, just. Okay.
I have a question about the very first step. So
Yeah.
you don't really have a concept of inverses of this one.
No.
So why do we know that if we keep on taking the left powers of 1, the first time we repeat it's going to be 1?
No, we just assume that this is possible. So now I ask, is this operation self-distributive?
Sure, but why have we ruled out the possibility that the powers of 1 are 2, 3, 4, and then 2?
Yeah, we could, but that would give you another law. Well, it might be that there's also a left distributive, but it wouldn't have certain characteristics. So it wouldn't have, for example, this row. I will now give some. I will some theorems. So Paul.
So sorry. This question is that there could be other.
Other finite left.
Self-distributive, finite.
Yeah.
Left distributed finite operations with 1 generator other than this.
Yes. I don't know if with 4 you can get, but with other numbers you can get. With bigger numbers you can get other. So for example, I think that there are like 2 by 2 matrices. You get 3. There are 3 left distributive algebras.
But there's this extra condition that they want
1 generator. Yeah, but with 2 by 2 it's easy. You cannot.
Sure.
I think yes. With 2 by 2, they will have 1 generator. I think.
But what you're saying is that a Laver.
Sorry.
A Laver table is one that looks like this.
Yeah.
So it's left distributive operation.
Yeah.
You have 1 generator finite. You have 1 generator, and this generator is going to be. It gives you something different. And once the first time it gives you something you've already seen, it's actually the generator itself.
Yeah.
And that's a Laver.
Yeah.
A Laver.
Actually, so I'll be more precise in a minute. So, well, let's try to do the, so is this left distributive? Is T4 left distributive? Well, you know, if you recall something I said last month, then the answer is yes. I will recall afterwards what I said. So let's do this with n equals 3. 1, 2, 3. 1, 2, 3. So we do 2, 3, 1. Now I've told you how we do this. We go at column. Column 3 plus 1 is 4. 4 equals 1. So we'll look at this column. And then 1, I go to the first row, it's the 2. We'll go to the second row, it's the 3. It's done. I look at 2, I go to the third column. The third column only has this number. So it's this. And then first I go to the second column. And then 2, I look at 2, it's a 3. And then 3, I look at 2, and I have here a 2. Now let's try. We want to see if this is left self-distributive. You can guess what. So 3 times 3 star 3 is 3. 1 star 3 is 2. And the left self-distributive log would give us 1 star 3 star 1 star 3. But this is 1 star 3. It's 2. And 2 star 2 is 3. These are different. So this one is not left self-distributive.
Oh, is it n called? Is the rank?
No, I'm just using it capital N to just cardinality of the algebra.
So you're going to make a claim that a Laver table, the cardinality is.
Yeah. Yeah.
And that's enough?
Yeah. So proposition by a guy named Laver. The tables are left distributive, if and only if n is a power of 2. So 4 is a power of 2, 3 is not. And this is how I knew. Now, this actually, Verhulm did not give the right proof. So this should be said it's Verhulm corrected by a guy named Drapal. He gave the right. So the notation for these left distributive algebras is just AN. So this is the cardinal algebra of cardinality 2 to the n. So the cardinality. And I will call Laver table just these. Now I'm going to give you some facts that they are not important for what we want, but this is just general culture.
And just
Yeah.
this is an elementary. says that it doesn't use much.
Yeah, completely the most. I think like induction for delta zero with at most. And well, I'll give you. I'll just put these propositions. They have. I'm not giving them by the right order or the right logical order. It's just something interesting. So another proposition by Grapal is that if you have a finite, if you have B, which is finite left distributive with one generator. If you have an element which is a left identity with left identity, which is the case of Laver tables. So you always the last row. Then it's also well then B is isomorphic with some AM. So we can characterize the finite left distributive of algebras with one generator. These are the ones that have a left identity. And by Grapal also, if you again have finite left distributive one generator, a left identity implies it's right. I don't know if this is terminology in English, but it's right absorbent. In Portuguese, we would say absorbent element in the sense that B star A equals A for all B. So left neutral, and this is why this table here, we had a problem here. This 2 should have been a 3 for us to get a left distributive algebra.
No, I don't know.
So if you have a left identity, which is the case of 3, then that left identity should be absorbent, which means that this column should have been only 3s, and but it's not. So
And what's the assumption for this?
it's the same as above. So as above. So finite left distributive one generator and no, but this is not relevant for what we're going to do. It is just facts that may make it clear what's happening. Now this is more relevant. So this is proposition by Verhung, and again corrected by Grapal. All rows in a Laver table are periodic. And the period is a power of 2. So this is and another proposition is, and it's actually how we go about proving this stuff. It's that suppose you have n is smaller than some n prime, and you consider the projection from the bigger to the smaller, where to A, you consider A mod 2 to the n. Then this is a homomorphism. Homomorphism. Sorry?
Are you going to show anything?
No, this is just well, I can lead you to the papers, but it's just standard stuff, standard finite math. But actually, Verhulm got this wrong. So he thought that if n divides some n prime, then this morphism, this would be a morphism of algebras, but it's not true. So this is what Drapal corrected. This is true if Tn is a Laver table, then this is a morphism. So the proof that this is a power 2 uses this kind of things, that by you iterate stuff and then so I just said, so the rows are periodic, so let's look at them. In A0, so let's look at the first row in each algebra. In A0, so this is a 1 by 1 matrix, which is the row is just 1. In A1, the row is 2, 2. This is a 2 by 2 matrix. Now, if you go 2 mod 1, it's well, it's 0, but the 0 coincides with the 1 in this case.
What are you getting? It's the first row?
The first rows, yeah. So A3, we saw below that it was this 2 times 2, so this is the 4 by 4 matrix. No, sorry, no, this is the A2. A3 is going to be 2, 4, 6, 8, 2, 4, 6, 8. So this makes sense because 6 mod 4 is 2, 8 mod 4 is also is 4. So these things make sense. This is an 8 times 8 matrix. So I'm going to so these are the first rows.
So the period is just 2 to the n minus 1.
Almost. So A4, you're going to have 2, 12, 14, 16, and then it repeats. So tough luck. And then A5, it's 2, 12, 14, 16, 18, 28, 30, 32, and it repeats. So what are the periods of the so the first it's 1, then it's also 1, then it's 2, then it's 4 2 times, then it's 8, and then you can see that then it's 8 again, 8 again, 8 again, then it's 16, and it's 16, and you can go up to n up to 56. This is in this online encyclopedia of integer sequences. But as you can guess, you run out of memory. So you cannot go that far. You can. So here you already go. So there are ways of condensing the computation, but anyway, it's always going to. So when do we get to period? Sorry? Yes, because of the projections. Period 32. So say some wild numbers.
What's 16 up to n equals 56?
16 up to, sorry, what were you saying?
Yes, you're saying that at n equals 56, we're stopping at total.
Yeah,
Because it's from the.
yeah, it's 2 times 56 times 2 times 56 matrix.
Really surprising if we get that far, but okay, let's say. So, and you're saying that it's just 16, 16, 16 all the way?
Yeah, from 9 to 56, it's always 16.
So now you're asking,
Yeah.
is the answer no?
I'm asking you to give wild numbers.
So there's some lower bound, no, it's not.
Yeah. Well, oh, can be more creative, like 1,000 times, for example.
No, it's more than this.
Really? This is now it has the potential to be like the biggest number that will ever appear in a math proof. It's it can also be that it never gets to 32, and then you can prove that large cardinals are the biggest large cardinals are inconsistent. But
Well, the only way to prove that is that Laver able means period 72 is for large cardinals. The only way
for the known way, the only known way is with large cardinals, yes.
Wait, so you're saying that, so you know that it's this big number because what?
I'll give you more concrete. So theorem by Dougherty. So this is an old, you don't get to, not until at least n equals, I'll just put the notation and then I'll F9, F8, F8 of 254. So what did I write? So this is a notation to express really fast growing functions. And they go like this. F0 is n plus 1. This is related to the primitive recursive hierarchy. So fp plus 1 of 0 is fp of 1. And fp plus 1 of n plus 1 is fp of fp plus 1 at n. So each function uses n many times the previous function. So if you go to Wikipedia or something, you can see that f1 is just n plus 2, but then f2 is 2n plus 3, and then f3 is going to be 2 to the n plus 3 minus 3, I think. But the important thing is here you double, here you exponentiate, and then when you get to f4, you get 2 to the 2 to the 2 to the 2 n plus 3 times. And we have here a minus 3. So this is super exponentiation. F5 is going to be iterated super exponentiation. 6 iterated that, iterated that, iterated that. And then you get to F8. Now F8 is going to be fed with the number 254. But that is going only to be used to see.
Stop, please. Right, so we can't even conceive of the number.
Yeah.
Right? So it's more than anything, it's inconceivable.
No, well,
I mean,
there are many numbers that have appeared in combinatorics that are bigger than this. So, for example, Graham's number. Graham's number would be something of this kind. It's not exactly this because it has 3 variables, but the growth rate would be beyond so f omega is what's called the Ackermann function, and then this is an iterated Ackermann function. But this continues with all the ordinals up to a point.
so this is less than the Ackermann function.
Yeah, so this is primitive. Yeah, no, but in the same paper, Dougherty proved that the periods. So the time you have to wait between periods grows faster than Ackermann. Yeah. But it wasn't known for more than 30 years if you could improve this, and now if it's correct. There's
So that should imply something like it's already independent, there's some finite theories.
Yeah, so for example, primitive recursive, it's what you get with induction for sigma 1 formulas. So it's a subsystem of piano arithmetic. The growth rate is going to be even much bigger than, if it's correct, there's a Chinese guy in Australia, no, in New Zealand, who seemingly proved that they go beyond everything you can do in piano arithmetic and even stronger theories. And this is unlike, for example, Graham's number, which is an upper bound. This is a lower bound. So it's going to. But see how these things are formed. They are formed really from a really recursive way. You can't get more simple than this. So the purpose of this talk was to talk about the theorem.
If this large cardinal is necessary, does that also imply that the lower bound is like enormously bigger than?
Yeah, well, I think the proof theorists can answer that better than I, because I don't know exactly if there's an equivalence between center orderings and the growth rates, if it always works, but in principle, yes. But it's
what is the question?
The question is, suppose that you need this large, it might even prove that. With a smaller large cardinal assumption, it's still in the 0%. Then it would follow that this number is like huge.
in principle. So it's with the known techniques. So if you add to the theory all the true pi1 sentences, then it should be the case that the kind of independence it's related with growth rates. But if you don't throw in that, I don't know. So the theorem is that the periods of the rows tend to infinity. The periods of the rows tend to infinity. Under the assumption of the large cardinal axiom I3, which I will describe. So you want to have a break or?
Maybe half an hour more.
Okay. So my second section is large cardinals. And the first is the subsection, which is the von Neumann hierarchy. Von Neumann hierarchy. Ring. So this part is not going to be so interesting. So this is, I have to give you the definitions of set theory. So it's going to be definitions and observations, basically. Before I should tell you what's going to be the strategy for the theorem, which is actually a strategy that also appears in theoretical computer science. Which is, so you want to prove that the search for something terminates. In this case, you want to prove that the search for a change of period terminates. What you do is you go by contradiction. You prove that there's going to be an infinite descending sequence of entities for which infinite descending sequences cannot happen. For example, and this is in theoretical computer science, there's this subfield which is called term rewriting systems, and this is a technique that they use. So they don't use large cardinals, but they do use what I'm going to ordinals. So get ready. There's going to be definitions ahead. So suppose you have a totally ordered set. So it just means that situation is transitive and you have trichotomy. So either A is smaller than B, or A is equal to B, or A is bigger than B. So A or A equals B, or A is bigger than B. Then a totally ordered set is a well-ordering, is well ordered if for every y containing x that's non-empty, there is a minimum element, y minimum of capital Y. And the easy consequence of the definition is that if X is well ordered, there is no infinite descending sequence chain. So it cannot happen. It is an if and only if you assume choice, the axiom of choice, a weak version of the axiom of choice. But you can take this as definition. No infinite descending chains. And an observation is if Y is contained in X and X is well ordered, then Y is also well ordered. Ordered. This is just an observation. Why this is well ordered? And this is obvious because so any subset of Y is also a subset of X. So it's as a minimum. Now another definition. And then I go to examples. No, actually, well, two definitions and I go to examples. I say that a set M is transitive if for every X in M and for every Y in X, we have Y in M. So the idea is if you have Y, then Y is also in M. The idea of the transitive set. So the idea is that M has access to its own elements. Although, this is more like reviewing stuff. Yeah, so I just I'm not going to use this in practice, but it's I have to build the intuition what's going to happen, and a set alpha is transit that if you have an alpha that's transitive, sorry, no. If a set alpha is transitive and all of whose elements, all of its elements are transitive, then it's called an ordinal. So I'll give examples. The most trivial one is the empty set. So it has access to the elements of its elements because it simply doesn't have any. my curly brackets, they all look like right curly brackets, but you should look. Do not be. There are also left curly brackets. So.
Can I just ask one thing?
Yeah.
So you have this definition of ordinal. Of course, sooner or later you're going to say that ordinal with the absolute relation.
Yeah.
Is going to be well ordered. Probably that needs foundation. That's a question. Okay.
Yeah. But it's just that this I don't want to lose much time with definitions. So we can build the numbers by recursion. I should put this 0. 2. I have 2 here. So imagine that my curly brackets make sense. So you can build all the finite ordinals, and so any n. So finite numbers can be seen as ordinals. So they can be built from nothing, just with curly brackets and the commas.
Can I make just a comment?
Yeah.
Because this, there was a talk a long time explaining this. Non-ordinals, finite ordinals. It's a natural number, it's a set of expressions.
Yeah, so this is quite used in combinatorics.
That's how it's built. Natural number is a finite set, which is a set of predecessors.
Yeah. So in combinatorics, you also use this notation usually for the set of predecessors, or sometimes from 1 to n. But so in set theory, you don't even have to do that, because by definition, numbers are made from their predecessors. And then you get to infinite ordinals. So, and then, but you can go further and continue this process. And this continues forever. So, but this is just to build a bit of intuition. So now I have a fact, which is the membership relation. The membership relation. Oh, it's a binary relation. Makes this into a well-ordered set. This well-ordered. So to see if a number is smaller than another, you just see if it belongs to it. And so,
In that definition, it should be like hereditarily transitive of an ordinal. So not just all its elements are transitive, but their elements are transitive.
Yeah, that will follow from by what's called well-founded recursion. It will follow that yeah, if it's transitive and its elements are transitive, then the elements are also transitive. Then the elements of the elements are also transitive. No, actually, it's direct, because so suppose if you have gamma in beta in alpha, then gamma is also in alpha, therefore it's also transitive. But
An element of the ordinal is.
yeah. And this is all to build just this fact that given if one has a well-ordered set, then there is so well-ordered then there is a unique ordinal, and that's isomorphic. And this ordinal is called the order type, or the type of X, which I will abbreviate with this OTP of X.
I remember when I was maybe in my last year of
With the Antonio mentioned.
I did a course with Antonio Fernandes, but around the time I read a book by Cantor.
Which? I know.
I think this was written before the big crash. So it's very nice, and he actually defined ordinals as so for him an ordinal was an equivalence class of well-ordered
Sets, yes.
sets. So it's like so, and that's also still how we think of an ordinal. So just think of a set where you have an order relation and everything is ordered and there's no infinite descending chains. Now abstract away what the elements are and just think of the chain inequalities, right? There's this thing which is less than all of these and bigger than all of these, and you just think of these dots and in succession and they're ordered. That's an ordinal. That's how you should think.
Yeah. So this is just something that's helpful. Like a cardinal, it's also should also be an equivalence class, but we identify cardinals with specific ordinals because it's helpful to accelerate what we want to say about.
You didn't forget the order, but in the cardinal you did. You just it's anything. So it's any two sets for which there is a
bijection.
A bijection.
But you basically you choose one, a special one. But I'll talk about that afterward. So now I talk about. I'll just say what's the von Neumann hierarchy. So it starts like this. So the universe of set theory has this shape. So it has a column made from the ordinals, and then it has several. It's built by recursion the following way: V0 is just the empty set, and V alpha plus 1 is the power set of V alpha. And if we have a limit ordinal, so a limit ordinal is something like this that doesn't have a predecessor. We just do the union of the I use the alpha smaller than gamma. Gamma limit. So here, we start with the empty set, and then we add stuff, and eventually we get to V omega, which is so below this we have what's called a hereditarily finite set. So it's everything you can build from curly brackets and commas, but afterwards you cannot build them exactly like this. You get infinite elements. So with this, we can say that. So this is okay. The proposition. So if alpha is smaller than beta, then V alpha belongs to V beta, and it's contained. So these V's are transitive. The alphas are transitive. So I'm building by iteration. I'm building the universe of set theory.
To prove that you need induction, right? I mean, you need induction of the order.
Yeah. But I'm not. So this is really a crash course on stuff. So for any set X.
Can you just remind me what induction of the order is?
So well, we're not going to need it. It's just that
That's just
if something is so the regular induction is if something is true for 0, and if you can prove that if it's true for n, it's true for n plus 1, and it's true for all n. It's a regular induction. In here you prove the same. So if it's true for 0, if it's true for alpha, and it's true for alpha plus 1, then but for the limit gamas, you say that if it's true for all the predecessors, it must be true for gamma. If you have these preconditions, then it's true for every order.
That's basically complete induction.
complete induction.
It's
If you can show that it is true for alpha, using the fact that it's true for every element less than alpha, then it's true for it.
Right.
so as I said,
In the natural numbers, you only need the previous one, but here, all the ones that didn't have specific ones.
I see. So I can also think of the ordinals as being built like this, right? The next one, I can always do +1, right?
Yeah.
And eventually.
but you have limits.
I
So
mean, the ordinals are a generalization of the naturals. The naturals are the finite numbers.
Right,
The ordinals are the transfinite numbers.
right. But you know that there's also this issue with notation, something big on notation. But I should always think of it like this, because there's also limits of limits, right? So
yeah,
I can get omega, and then omega +1, and omega +2, and then I get 2 omega.
yeah, omega time plus omega,
Omega
Yeah.
plus omega.
and then omega times 3, omega to omega, then omega to omega to omega.
No, I still get omega squared.
Yeah,
And this is like confusing now because you have several limits, all of them are limits, but now you take the union of all of those, and that's your omega times omega.
yeah. So omega times omega is the sup of the omega to the n.
No, times omega. Omega squared.
Omega square is the
It's the sup of
it's the sup of the omega times n.
yes. Right. So each of these is a limit ordinal, and I've put them all in one set, and I axiomatize there's a supreme. No, I think the union, right? And that's
Yeah, the unit. Yeah.
This wouldn't be how it's usually defined, right? It would just be because there's no union, there's no simple choice for which ones to take the limit of. Like I could have also taken supermom omega times n +1, and that will still give me omega squared.
Yes. Yeah.
So
Yeah. There's no.
natural.
Yeah.
It's just
Well, there are several characterizations. So people in proof theory, they have this ordinal notations. So it's basically you start with the naturals and you organize them in such a way that the order type will be one of these things. And again, so this is used in term rewriting systems. The way you you associate terms to, or you associate ordinals to terms. This is how you then prove that certain searches terminate because you don't have infinite descending sequences. So I said any set is somewhere here, and the place where it appears, we call it the rank. So the rank of X, so I'm going to write like this, rank of X, R, is the least alpha such that X is contained in V alpha, which is equivalent to least alpha such that X belongs to V alpha plus 1. So some observations. Then I guess we do a break. So observation 0, the rank of alpha is itself. We can talk about for any A and B, we can build the ordered pair in the following way. So ordered pairs are a certain kind of sets. So if gamma is limit, then V gamma is closed under ordered pairs. And if I have a function, and he said there, if a function is defined by their graph. So a function also has a rank. So for example, so you have X containing some V alpha, Y containing some V beta, and both are smaller in some V gamma, smaller than gamma. Then you have F in gamma for gamma limits. So for gamma limit, V gamma is closed under functions between its elements. Between its elements. So you can think these are like when gamma is limited. So these are like mini universes.
Its elements. I mean, if X and Y is an element of the gamma, so is any function from X.
Yeah, and the set of functions is also an element, and so I think it's can do a break. 10 minutes. So let's say at 3:40 or 3:40. Yeah.
The gamma.
Anything in the gamma is actually in quantity of
Yeah, suppose so. suppose the maximum of these is alpha prime, then f belongs to v alpha plus 1, and the set of functions belongs to v alpha plus 2, for example. Oh. So just say enough.
So what's left to do?
So I recall, so there's this section was phenomenon, the phenomenon hierarchy. So the purpose was just to tell you about these sublevels of V. Then I have to recall the large cardinals that I spoke, which I'm going to do today. The large cardinals that I talked about last month. Then their connection with Laver tables, and then the proof of the Laver's field theorem.
You think the next two things today? Connection.
If you
Well, if we stay till midnight, if we were thinking, but let's say in an hour.
yeah, no, in less than an hour, yeah.
Okay, so let's do that. So basically today's kind of the intro. Now we're going to do these
The large cardinals, yeah.
Like three axes.
Yeah.
And then you're going to do what's the connection between these axes and the Laver table.
And Laver, yeah.
And then on next time we meet, you can
yeah. Yeah.
Right?
Yeah, and the proof 20 minutes it's done. So
It's 40.
yeah.
You always say. Okay.
So it's just so definition. So now it's just something in logic. So I'm not going to define what the language is. If you know what it is, good. If you don't know, then I'll just explain something. So suppose you have models of some language, L.
Right, this is gonna need some kind of introduction. Francesca does not know what that means. Or do you know what a model of a language is? Like, that's like.
Okay, I think.
I'll just give the intuition.
Yes.
Yeah,
So
what's a language? I mean, you don't have to give the precise definition,
Yeah.
but
so in a language, you just have, so you have symbols, for example, plus, times, smaller. You have variables, and you can define anything using and, or, negation, and what? And then the quantifiers. So everything that you can write with the variables, some operations, some comparisons, and then negation or conjunctions and quantifiers. So everything you can write.
that would be a formula. Right, it's not a language, right? So
So
formula.
these are formulas.
Right, so formula is something you can write with these things, right?
Okay, you know what it's a language, I'm not sure what you mean about models.
Yeah, we're gonna get it.
Okay.
So, but a formula is, you write quantifiers and the latent symbols and variables. Right, so, and there might be a constant also, like one, right?
Yeah.
But using these quantifiers, you can say things like, x equals y plus z. Right, or x is less than y plus z, and z squared, you can write things like this, and there exists a double set. So you can write things like the number is prime, and you can out of these basic constructs, you can write essentially any statement that we know and care about. And that's a state. Right?
So were you your undergraduate studies were on math or computer science?
The science and
Okay.
But have you studied like these formulas?
yes.
Yeah.
Yes, language, yes, I was not sure.
So these are formulas. Now, what's a language in Luis's sense? It's a collection of formulas. Am I right?
Yeah, so it's well formed. So the parentheses only rule is parentheses must make sense. Must be matched. So you must have a.
Oh, for a formula?
Yeah.
No, I'm assuming you understand that, right? So you have, of course, you have to put them together in a reasonable way, right? It has to mean something. So it's gonna be a tree and right, so the nodes of the tree will have stuff like that. So it's a nice, well-formed first order logic sentence, and a language is just a collection of these statements. Maybe there's some, it's closed under, no, nothing, not even.
No, it's just everything you can build. Well,
and you take
it's as well.
As your true statements. So these are the statements that you think should be true. Okay.
As if you're saying,
Am I thinking?
theory, not like.
Oh, that's a theory. Oh, that's not a language.
Yeah.
Oh, so what's a language?
No, the language is just a set of formulas.
Oh, I see. I think it's theory. What's a model of a language? Then I don't
It's an interpretation of language, meaning you have to interpret the domain for the variables, you have to interpret the relation symbols, if you have R, binary relation symbol, you would say
So-
X Rx, Y means X plus the Y.
So a group.
It's an interpretation. Language is syntax.
You give a meaning to the symbol.
Yeah. So if you are, yeah. So you have to say things like for every X, Y, and Z, X times Y times Z equals X times Y times Z. So this is a formula in the language, and this satisfies this thing.
No, wait. So now so what's the language? Then the language is the collection of all well-formed formulas that you can.
Yeah. Yeah.
Okay, so what's a model of the language is?
You just interpret the
It's a basic.
the operations and the relation.
Right, so a model of the language is a set,
Yeah,
right? Together with some operations on that set.
and relations.
Together with some operations and relations on this set. And this allows me to interpret when I see a formula. When I have a model, now it's saying something about the model.
Yeah.
Right, which might be true, might be false,
Yeah.
but that's.
So and usually we use this symbol phi for a formula. So the formula has variables. So for example, here, if you forget this quantifier, it had three variables, X, Y, and Z. We say for
So that means that if I have a language and a model, I can say the set of all sentences which are true in this one.
yeah,
This is something I can comment on.
yeah.
Because now each formula has a meaning, and this will and it will be either true or false.
But that will not need the notion of theory. We use this in yeah. And so there's the symbol saying that M satisfies something. So this means that M satisfies the formula. For example, if I have this.
So these variables are the three variables in the formula.
Yes. So if I had a group and I substituted here X, Y, and Z by any elements, A, B, and C, then they would satisfy this formula.
Right, but then you just write G satisfies phi, because there's
Yeah.
no.
Yeah,
There's no-
if you have sentences, then it's just five. So the definition that I wanted is just if you have so if you have a map from a model into another model or function, we say it's an elementary embedding if whenever you have elements in M and you have a formula which depends that has these variables that are not quantified, and you say something about these elements in M, then that is also true of their images.
Is it like, like a morphism of sorts? And now what you want is the morphism has to preserve truth.
Yeah, true statements must be preserved.
Is it something like in the category of mono or something? Is it a mono?
So if you're talking about categories, you have functors. So in categories, you have the objects would be models, the morphisms would be things of this sort. And but between categories, what you have is functors. So functors, they preserve.
Between categories, I'm thinking of the category of model.
Yeah, yes.
Language, yeah.
Yeah.
There would be a morphism in that category.
Yeah, so you can do logic with just categories. So if you have the category of models of, well, this is, it's done all the time, say, groups, the category of groups. So the morphisms, well, usually you just ask for homomorphisms. So these are stronger. So this is, yeah.
That's what I'm thinking.
So you have to fix, in that case, you have to fix what's called the complete theory. So if you have a complete theory, then yes, I think so. The logicians know more about this than I do, or Mario. Well, Mario Edmund probably knows more about this stuff, about categories and. But it's but yeah, so if you have a complete theory is something that decides the truth of any sentence, then everything goes.
So I don't want to push it so that was the point. So the point was that normally when I see a morphism, the condition for it to be a morphism is much simpler, right? It's like the image of
Yeah.
The image of the operation is the operation of the image,
Yeah.
right? But here, the condition for being an embedding is much more stringent.
Yeah.
In that all true statements have to be preserved.
Yeah.
Implied.
Yes.
So in N, more things can be true.
Yeah. So usually, for example, if you have.
There is, can I
Sorry,
Yeah.
this is a good, right? This is a good.
I think what you take as a morphism, it's what we would call an embedding. And there is this for elementary embedding.
Yeah.
Elementary means that it's with respect to first order logic. So all things of first order logic are preserved.
I see.
So elementary means first order logic in certain situations.
And then already applies something like, for instance, that has to be an equivalence actually, right? Because
Yeah,
it
yeah.
always takes nouns.
Yeah, exactly.
I see.
So for example.
While usually it's just an embedding, it's just for quantified things.
Yeah, I see.
So for example, consider a group that's inside another group. So it's a subgroup. the bigger one may not be abelian, may not be commutative, and the smaller one may be commutative. So so take J as the identity. So there are elements, so it may happen that there are elements here that do not commute with elements in the bigger one. So in this case, the identity would not be elementary.
I see. I see, because of course, because although, you know, with themselves, they commute and everything, and you just get that from the morphism. Once you add once you add this thing, you know, if there was an identity in the smaller group, it also needs to be an identity. Or
Yeah, exactly. Yeah.
or everything, so.
No, so in particular, so if you have sentences, so they don't have, so M and N have the same theory. In particular.
Which gave a good example, but maybe another one is just Q inside R, the rationals inside the reals. That's embedding, but it's not elementary because in R you have the existent x whose square is 2. Q with the rationals you don't have it. Tells one from the other in the first order way.
I see. So from a naive person who's never seen this kind of thing, I would say, well, just M equals N then, but that's actually not true. There's actually.
Then we would say if all elementary truths are the same, they are the same model of isomorphism.
Right.
This would be the case if it was all truths, but only the elementary truths expressed in first order logic, so it doesn't make this correct. Non-isomorphic models can have the same elementary truths.
So that could be, for instance, a second order sentence.
Oh yeah, you could tell them.
That tell them. Right. So if I can quantify for subsets.
Yeah, that's a strong set. That's a strong set. And
Oh, yeah. I think I nuance there.
So, so we can, as an so we can consider elementary embeddings from different sections of the universe. And so, and suppose you have some function in V alpha. So some function from x into y. Then J of f is also going to be a function. It's going to be a function from J of capital X to J of capital Y. Because you can define what are functions in the language of set theory. You can define any mathematical object in set theory, basically. So consider J. I'm now restricting, so I'm not considering any. I'm not considering these things. I'm just considering the membership relation. The membership relation describes every mathematical object. Any mathematical object can be described by the membership relation. And being a function is something that you can describe in set theory. So the image of a function must also be a function. And the domain of the image must be the image of the domain. And the target must be the image of the target.
What do you mean why? Sorry, that's
So
why wouldn't you be able to take a function and kind of
Suppose the alpha says f is a function
That
from x to y.
no, but you're assuming x and y can be defined using formulas, which
No. These are if f is in alpha, the domain and the target are also defined. So x is in the alpha and y is also in the alpha.
so both f in this formula, both f, x, and y,
Yeah.
or
So I should have probably, it would have been less confusing
so
if I
in
just
that
wrote that.
formula, both f, x, and y are these a1, a2, a3 that appear
Yeah.
in the other.
So then V beta says that j of f is a function from j of x to j of y.
So when you write this, you're writing f, x, and y explicitly in there.
No, so they don't have to be definable. These are just for so
X, Y, and F is like the A thing.
Right.
It's just parameters, just no answer.
There's like an x1, x2, x3. You take x1 is equal to x2, x3. It's like here's a formula phi of x1, x2, x3. This is the statement.
Yeah, that's it's a statement with three parameters.
and what happens to the values? So what happens to well, it's the same thing. So j of f of x is going to be j of f applied to j of x.
Oh, yes. Oh, that's formula, right? So
Oh, don't try to think too much about it. Just
So you're saying because I can write this statement f of x equals y as a formula, right?
yeah. So j of y.
You're just writing x comma y is in f. Right?
So I say y is the image of x under f. Then v beta is going to say
So you need to show that this statement, y is the image of x under f. You have to write it using your language, I guess,
Yeah.
right? So I guess it's something like there exists a z such that z equals the pair x,
Yeah,
y,
exactly.
and z is an f.
Yeah.
I mean, certainly you could say it's.
Right, I know, but I'm just, yeah.
So this is the pair x y belongs to x.
If the pair is in your notation, then
Yeah.
that's fine, but if the pair is not in your notation, you can unfold it.
Yeah.
Right.
There's j of y, j of x, j of f.
And this is the connection to that distribution.
Yeah. Wow, you were really fast. So now I have to define the critical ordinal. So we talked about this last time. So consider J that's non-trivial. Non-trivial. Non-trivial means just that it's different from the identity. then there is a first ordinal that is moved. That is moved. What do I mean by this? So there's going to be a gamma. So I'll call it gamma. So J of gamma is bigger than gamma, but J of sigma is equal to sigma for every sigma smaller than gamma. So and we call this the critical point. The critical point of J. And we write crit of J.
Rank is also accessible in the notion of rank.
Yeah. Being an ordinal is everything in mathematics is expressible with the membership relation. And then last month I proved, but here I'm just going to state it, that the critical point of J, the alpha to the beta of this is an inaccessible cardinal. I don't remember if these has two ends, so it's just a blank. Charles, I don't know if he's still online or not. So what does this mean? It means that if you have sigma smaller, then the universe up to sigma is smaller than gamma. So this is the thing that you were talking about the cardinals and the ordinals. So you can think of so basically there's going to be a bijection from this part of the element into an ordinal that's below gamma. And the second is if you have some x in V gamma, and you have a function from x into gamma, then the sup of its image is strictly smaller than gamma. So these are the two only things that I need.
Sorry, why is this ordinal called cardinal? An ordinal, right? So why are you calling it a cardinal?
So because cardinals are special kinds of ordinals. So cardinals are ordinals that cannot be in a bijection with a smaller ordinal. But you don't need to know that. You just need to know that the size of the universe up to something smaller, it's still smaller.
So these 2 points are properties of
Inaccessible cardinal.
Is it the definition or?
It's equivalent, yes. And then last month I proved a theorem by Kuhnen. Yeah.
That is my intuition. So the supremum of all the range of f is smaller than gamma.
And gamma. That's not always true. For example, if you have v omega plus omega, then you have the following function from the naturals into omega plus omega. So to each n, omega plus n.
The supremum is equal to.
And in this case, the supreme is going to be omega plus omega.
I thought that this should hold like generally that as long as I have an infinite sequence, I should be able to reach any limit.
Yeah, so you're thinking what's called a regular cardinal, but there are cardinals that are also singular. So, but I didn't want to speak to be so to talk about that. But yes, your intuition for what I want to do, your intuition is correct. So it's not so omega plus omega is what's called a singular ordinal. So here this is the definition of a regular ordinal. But so I didn't want to erase this, so I'll write this afterwards again, or I'll write Kuhnen here.
I have one question.
Yeah.
Right, so you had written down the definition of a critical point.
Yeah.
And you only looked at ordinals for defining.
Yeah.
Is it the case that if my mapping has a critical point alpha, so everything smaller, its identity on the ordinals of there, will it also be identity on V of those ordinals? Will it also be identity on the von Neumann level at that ordinal?
Yes, below it's the identity. Yes.
Not just on the ordinals, on the whole. So because the way you defined it was just using ordinals.
The critical, yeah. Yes, because every set has a rank, and so and you can prove by induction that so you need to prove that the so you need a technical condition, but the idea is yes, it's the identity because of the ranks. So if not, there would be a least rank that would be moved, but then the elements of the elements would still be equal, and then you would get a contradiction.
The rank of J of something should be equal to J.
Yeah, to the J of the rank. So Kuhnen just proved that. I'll write it just here. So there is no J from V alpha plus 2 into V alpha plus 2. So the ordinals here should be bigger. Either well, they are usually bigger than the ordinals here.
It's very interesting. So you defined what a critical point of an embedding is.
Yeah.
And it follows that it has this property that it's in an inaccessible card. Okay.
Sorry, there is no J that different from the identity almost.
Oh. So there is even, you're saying, why is there equals 2 there? Because it's not true for V0 and V1.
It was the technical thing. So it was the proof that I gave. So you can go, so I'll write here what we can. So the large cardinal I3 is the large cardinal hypothesis that there is no non-trivial J-com. I'll use lambda with lambda limit. And so I'll drag.
Sorry. Can I try to? I still don't understand the theory of Kunin.
Yeah. So if I do the picture, it might be more understandable. So call kappa the critical point of J. Then everything here is equal. Then kappa goes to J of kappa. And J of kappa itself goes to J of kappa. Well, this is J kappa. The square of kappa is going to be J cube kappa. And then lambda is going to be the supremum of all of this stuff. What cannot happen, so suppose alpha was lambda, what cannot happen is that the embedding goes up to lambda plus 2.
Sorry. Can I help me? So the theorem of Kunin says for all alpha. Then it says
Yeah, for
alpha. Does not exist a non-trivial elementary embedding of the alpha plus 2 to the alpha plus 2.
yeah.
So what can I? So I can deduce. So if I have an elementary embedding from some v alpha to some v beta, from this theorem I can conclude two things. Either alpha and beta are both
Different?
Yes.
No, but in that case, it also doesn't work.
Omega plus 1. Omega plus 1 makes sense.
Because finite numbers are definable. You cannot move them.
This whole doesn't really affect.
Oh, I see.
Above the limit.
I see. So either thank you. That helps. So either alpha and beta or a limit ordinal or a limit ordinal plus 1 at most. Right? That's the first possibility. Or the other possibility is well, beta is bigger than alpha.
Yeah.
That will be enough.
Yeah.
So, and that's so these are the possibilities that are left.
Yeah.
And now, are you telling me that? But
The I3 is just this.
So that's another statement. There exists in monotrivial something.
Yeah.
You have an extra no in your statement. It should be I3 is the statement there is such an
Sorry?
I3 is the statement that there is such an embedding.
There is no.
Sorry. There is.
Okay.
Sorry.
Now,
So okay, then now it makes sense. Yeah. Sorry.
okay. I see. So from the theorem of Kuhnen, a question can come is. Oh, I see. So you leave open the possibility that there might be an embedding from V alpha to itself, a non-trivial one.
And also,
If it's a limit, right?
yes, so I talked about also this is a stronger large cardinal hypothesis, V lambda plus 1 into V lambda plus 1. But definitely V lambda plus 2 into V lambda plus 2, no.
Is it like, for instance, is there trivially always one from V alpha to V alpha plus 1?
No.
Why?
No, because the critical point is always an inaccessible. So an inaccessible cannot be proved by the axioms of set theory. No, so if I have whatever alpha and beta are, if the critical point is always inaccessible. So I cannot prove that there are any alpha and beta for which there is an embedding. Yeah, because the critical point would be a large cardinal, and we cannot prove that large cardinals exist with the normal axioms. So they form a hierarchy.
I think I understood what you said. I don't understand why it implies that V alpha could not be embedded in V alpha plus 1. I don't understand. So that term is saying something, right? I cannot embed.
In your case,
I cannot embed alpha plus 2 into alpha plus 2, right? That's what you're saying. But that leaves open some possibilities, some things that might be possible.
yeah.
Maybe I can embed the alpha plus 2 into the alpha plus 3, say, or what, or not.
But in your case, so suppose you have this. This doesn't sound right. So definitely you cannot do alpha plus 1 into the alpha plus 2. Well, you can, no. No, here, no, sorry, you can. What you were saying, because trivially, so if you have J from V lambda plus 1 into V lambda plus 1, then the restriction to V lambda obviously goes from V lambda into also V lambda plus 1. But actually, we know that it actually just goes to V lambda. So yeah, so what you were saying is it's possible. But what's going to happen is that alpha is not going to be moved.
I see. So
in this case, J of lambda is lambda. It's actually the first fixed point above all the first fixed point above all of these is going to be lambda.
Okay, so this only makes sense, exists if alpha equals beta, then. This existence of a non-trivial embedding.
No. The smallest is something like this: V kappa plus 1 into V J kappa plus 1. So it's the smallest of these kind of large cardinals.
I'm having the same problem I had on the.
So suppose and kappa is the critical point of J. This is a small compared
with I3, compare with I3. And this is what's called a one extendable cardinal. It's below what we call supercompact, and above what we call measurable. It's nothing.
So in that particular embedding, all the ordinals are preserved except for k plus one.
Yeah.
Except for
No, so alpha smaller than kappa, J of alpha is alpha. But then J of kappa, J of kappa, kappa goes to J of kappa, which is bigger. Right.
right, so now basically so it says there's no trivial embedding.
You can have, and if you put two, this is also possible. And put here 2 kappa plus 2 into J kappa plus 2. This is all possible. But it's still very small compared with I3. I3 is really, really much bigger.
Okay. All right, so I think I understand what Kuhn's theorem says. It says for every alpha I can have this embedding. And now what does I3 say? That I have an ordinal lambda, right? And I have an embedding, elementary embedding from V lambda to V lambda, such that lambda is actually the following limit. I start with k, the smallest moved.
Yeah, so it's going to be the first fixed point above the.
It's not obvious that it's the first fixed point, right? But so the first definition that you said is I start with k, I take the image, then I go to that, and take the image. I take the union or the union of these sets of the limit, and that's actually lambda, right? But is it true that also it's the first fixed point? Is that obvious?
Because of the Kuhn's theorem. Because if it was bigger, then you would restrict below, and you'd get a contradiction. But so probably the argument is trivial, but it's, I'm not going to try to do it because I may be wrong, but this must necessarily be the case. J of lambda is lambda. So, and it's not difficult, but
and you're saying it's
no, it's trivial because lambda is the soup. I give the argument of the last time. Lambda is the soup of the J and kappa. If you J of lambda is the soup of the Jn plus 1 of kappa, which is the same thing.
okay. Why is lambda necessarily a cardinal? Sorry.
Because it's the soup of cardinals. It's not important for what we do.
Just like.
Yeah, sure.
So why
The soup of cardinals is also cardinal.
Oh, this is a cardinal. All these are cardinals. Are they?
Yeah, so kappa is inaccessible. Its image must also be inaccessible. The image of the image is also inaccessible. The image of the image of the image is inaccessible.
I see, so there are, oh, so the inaccessibles are cardinals because the cardinality of anything below it is less than it.
Yeah.
So the I3 hypothesis says there exists a cardinal lambda, right?
Yeah.
And an elementary embedding J from V lambda to itself such that lambda is actually the limit as n goes to infinity of J of J of J of J of J of J of K n times where K is the least is
Yeah. You should say kappa, not K.
sorry.
Something I only learned when I went abroad.
Is
Because
this,
they say the same.
what you're saying is that there is a cardinal lambda, an elementary embedding from V lambda to V lambda, whose critical point is kappa, and lambda is the supreme of kappa, j kappa, jj kappa, blah, blah, blah. That's what you're saying.
Yeah, so from this follows. Because of Kuhnen. No, this follows just because of this.
I mean, you're saying there is a non-trivial embedding, so there must be a critical of.
Yeah.
And the lambda is the supreme of kappa, j kappa, jj
Yeah.
kappa.
This is the large cardinal. You want to stop here or with the Laver table? With the
Yeah, maybe that's fine.
yeah, all of us. So wrap up this ultra absurdly big stuff. Have a connection with finite math.
Right.